Hello, today I wanted to talk about how to design a common emitter amplifier. Topics I want to cover are DC analysis, AC analysis, and I want to briefly touch on frequency response as well as input and output impedance. I'm going to present a hypothetical situation with potential parameters and some practical design goals. And we're going to utilize theory and circuit analysis in order to meet those design goals. I always think it's easier to learn this stuff through a general example problem rather than, just reading a textbook aimlessly. I'd like to just kind of go over this reference sheet that we're going to be using throughout the video. This is the common emitter amplifier configuration. These are capacitors that are used to either couple stages together or couple the function generator to the input of the amplifier and couple the output of the amplifier to a load resistance or some other amplifier stage. This is the hybrid pi small signal model. It's used for AC analysis. It's also used to better visualize input and output impedance. RPi and RO, or little RO as we can call it, are internal resistance values. Their equations are given right here. RPi is controlled by any of the current values technically, but we're going to use the base current value, the DC current value. And then little RO is controlled by the early voltage value over the collector current value, which is also a DC current value. The early voltage is determined through the curve trace of any given device. I'm not going to really go into how it is determined or calculated, but just know in general it's around 100 volts. The magnitude, that is 100 volts, and that's the value that we will use. The base emitter loop is a pretty useful property of a BJT. This is V Thevenin and R Thevenin. It's used to represent the Thevenin equivalent circuit of this branch right here from VDD down to ground, including the R1 and the R2. V Thevenin is determined by the voltage divider that is formed by R1 and R2 with the power supply voltage. R Thevenin is determined by these two values in parallel. We can utilize Kirchhoff's voltage law to equate the potential voltage drop across the whole branch and set it equal to the sum of the voltage drop across this resistance, and then the voltage drop across the base emitter PN junction, which is typically 0.7 volts in forward active mode, which is hopefully the mode you're hoping to operate in. Here is the equation derived from this diagram right here. We'll use it later to determine this, the R Thevenin, and we'll work backwards to figure out R1 and R2. Okay, so let's first consider DC analysis. We're going to have a power supply voltage of 20 volts. Our device is going to have a beta or current amplification factor of 200, and we are going to try and design for a voltage gain of above 300. This schematic right here represents what we're going to be working with to perform DC analysis. It comes from this reference sheet I was just talking about. During DC analysis, we consider all these capacitors to be open circuits. So this is the resulting schematic. Just this. This extra notation is trying to illustrate the importance of choosing the proper VC and VE value, which is the collector voltage and then the emitter voltage. The collector voltage will determine the DC bias line that the output signal will oscillate on. It's limited at the top by the power supply voltage, and it's limited at the bottom by the emitter voltage. So we want to give the output signal some room to swing, so to speak. So choosing a VC of about half the power supply is is a very good starting point. And then also we want to keep in mind that we want to put some space between VC and VE. So we want it to be below VC, most certainly, but we don't want it to be too close. That's just important to remember as we are progressing here. The typical gain equation is given by the transconductance times the equivalent output resistance of the configuration. Expanding on this a little bit, and as shown earlier, RO is in parallel with the collector resistance. Little RO can be visualized right here. It's across the collector down to the emitter, and that's where little RO, that's where it lives. Okay, and it's given by, as discussed earlier, the early voltage over the collector current. And performing some simple plugins and simple algebra, we can reduce the gain equation to this right here. And as spoken about earlier, these are some predetermined values, and the thermal voltage is at room temperature is typically about 25 millivolts. Hopefully you're designing and building in an area that's at room temperature, and you can consider it to be 25 millivolts. Otherwise, you might have to make some special considerations. And then by Ohm's law, IC times RC gives us just simply VC. And as we spoke about earlier, we want to operate at a VC that's half of VDD. Okay? So, as discussed earlier, our early voltage is 100, VT is 25 millivolts, and we just decided that these values right here are both 10 volts. And plugging in and performing some simple calculations, we can see that theoretically we're going to have a voltage gain of about 360 volts over volts, approximately. Now that we have this value, we want to choose a collector current to operate at. Some typical collector current ranges is about maybe 5 milliamps to 20 milliamps. You really don't typically want to operate at the lower or higher end of that. So we're going to choose to operate at a happy medium of about 10 milliamps. And then utilizing Ohm's law again, we can determine that our collector resistance is going to be about 1 kilo ohm. And also for simplicity, we are going to call the emitter current equal approximately to the collector current, which again is just 10 milliamps. And then IB is, we're going to utilize the relationship between the collector current and the base current and beta to determine that our base current is going to be about 50 microamps DC. Now we're going to choose our VE, which we discussed earlier. We want to give some distance here. So to be safe, and you can choose whichever you want, but to play it very, very safe, we're going to call it 1/4 of our chosen collector voltage value. And that's going to work out to be about 2.5 volts. So our RE, or our emitter resistance, is about 250 ohms. So now moving on to the base emitter loop equation that we determined earlier from our reference sheet. And if you just want to see it one more time, here it is. In the sheet previous to this one, we changed this IE to this right here, so we can work with just one DC current value that we have already determined to be 50 microamps. But these equations right here can help you see the relationship between the emitter current and the base current, because it's not an extremely obvious one. Okay, so now what we want to do here is plug in our known values. We know this, and we know this. What we don't know is what we want our V Thevenin and our R Thevenin to be. So our first move is going to be to plug in what is known. And you can choose to do this on a calculator if you would like, but just to speed up the process here, I'm just going to tell you that plugging everything in breaks down to this. So what this tells us is what our Thevenin voltage minimum is, and that is 3.22 volts. That's because if we set it lower than 3.22 volts when we solve for RTH, we're going to get a negative RTH, which isn't real. It doesn't happen. So what this is telling us right now is we want to choose a Thevenin that is above 3.22. And also, to be safe, we're going to say we want it to be at least 2 times Thevenin minimum. Okay? And we're gonna multiply that by 2, and we're gonna round up a little bit to an even 7 volts. It's just a nice and easy number to work with. Plugging that in and solving for RTH, we have 75.4 kilo ohms. Okay? Now that we have this value, we can start solving for our R1 and our R2. We are going to kind of arbitrarily, well, not so much arbitrarily, but we're going to choose an R1 that we would like to work with. And just FYI, typical R1 and R2 values are between 100 kilo ohms and 1 mega ohm. That's just standard practice. So we are going to choose R1 to be 220 kilo ohms, just because that's a nice, easy resistance value to work with, especially if you're building the circuit on a breadboard, for example. That's a 1 resistor value. As discussed earlier, our R Thevenin is just these two values in parallel. So RTH equals R1 times R2 over R1 plus R2. If we plug in this value that we just decided that we wanted to work with into this equation right here, and then we plug our determined R Thevenin value in here, we can work backwards and we can solve for R2, where we will get an R2 of 115 kilo ohm. Okay, so now we have just determined all of our resistance values that are going to properly DC bias our common emitter configuration. Moving back to our reference sheet, we can plug all these values in, potentially in some kind of simulation program such as LT-Spice or Multisim, and hopefully you are able to prove to yourself that you are able to design for a particular game. The process that I just went through right here is not the only way to do this. There are quite a few, and also the method you're going to use is going to depend on what you're designing for. In this situation, we're designing for gain. You might want to design for output or input impedance, for example, or you might want to operate at a particular collector current, for example. All these different things will implicate different methods. But in general, you can use all of the theory discussed here in any order you would like, and you should generally be able to get an extremely good foundation to begin being able to actually build an amplifier and have it meet design goals. And of course, this is all in theory. It might not work perfectly on a breadboard or anywhere else, but as discussed, it's a great place to start. So I'd like to just briefly touch on the input and the output impedance. Now that we have performed DC analysis, we can move on to the hybrid pi model, which is just in general AC analysis. And in AC analysis, all capacitors are considered to be short circuits. And it breaks down to this right here, which is just a very nice, clean, and organized circuit diagram to look at. This portion right here, as discussed earlier, is all the inner workings of the device itself, minus some capacitance values that are determined by the architecture of the device, which is obviously determined during fabrication. But the important ones we're going to look at is the RPi value, which comes into parallel with RB, which is just the R-Thevenin value discussed earlier, just different notation. These two values in parallel will determine the input impedance of your amplifier, which is important to know if you are using a stage behind this amplifier. You need to consider the output impedance of this connecting stage and the input impedance of this connecting stage. We won't discuss that now, but that's just for your consideration. And then RO in parallel with RC is your output impedance, as we've already gone into some pretty serious detail as far as how that affects the gain and the overall design. As far as frequency response goes, I'm not going to go too deep into it, but it's important that you know that this capacitor value right here is going to largely determine your low frequency cutoff. It's also minimally determined by these two values right here. Appropriate ranges of values for these capacitors, these two in specific, is 1 microfarad to 10 microfarad. And then appropriate capacitance values for here is about 100 microfarad to 1000 microfarad. If you aren't getting a good enough low frequency response, just increase this value right here. High frequency cutoff is determined about the aforementioned not included internal capacitance values. It's also determined by the overall gain of the circuit. So if you're building this and you need a better high frequency response, the only way you can really control that is by lowering the gain. And if you're trying to raise or lower the gain, in general, what you're going to want to do is make slight changes to this collector resistance value right here that, will be determined by all this again. But that's the value you want to mess with if you're trying to raise or lower the gain. And I think that about covers everything. Well, not everything, but it's a very good general idea of how to do this. I hope the video was helpful, and if you have any questions or want me to elaborate on any of this, please just leave a comment, and I hope you have a good day.